Hey everybody, I guess I lied at the end of last video. We're not actually doing the test yet. We're going to learn how to calculate the z and the p-values, and then the next one we'll put it all together. All right, so calculating the z and the p-values. So we're using some of the same information from last time. So Mr. Robeson made 32 out of 50 shots. The claim was made he made 80% of his shots. What is the p-hat? So the p-hat here would be 32 out of 50, like the actual sample information. How does his p-hat compare to p? Well, 32 out of 50 is what, 0.64 or 64%. So 64% is definitely less than 80%. All right? So it looks like we have evidence that it is different, but the question is, how much different is it? Like, we wouldn't expect me to hit 80% every time I took 50 shots. Like, sometimes it'd be a little less than 80, sometimes it'd be a little bit more than 80 if I'm really an 80% shooter. All right, but 64, that seems like a far way down from 80. But then again, 50 is not a large sample. So we're not sure really how it compares. It's less than, so we have evidence that my P is actually less than 0.80. But is it enough evidence? And that's what these tests do. All right, so we have some evidence, but is this going to be enough evidence? So what are the mean and standard deviation for the sampling distribution? All right, well, the mean for the sampling distribution of all the p-hats is going to be what we believe our p to be in the beginning, which is 0.80. All right, and here it is right here. All right, the standard deviation for all those p-hats, and again, we're going to take 80 to be our gospel. So we'll say this is p0 and p0. So what we're starting with is that p0 is 80%. So it'd be the square root of 0.80, 1 minus 0.80 over 50 was our sample size. And let's pull out our calculator here and let's work that out. So on second square root, 0.80 times 0.20 is what that works out to, divided by 50, enter, and we get 0.565. Basically 0.0565. That makes a big difference. There we go. So it's about 5-6%. All right. So then we want to know, or what we're going to want to know is, how many standard deviations is this 64% or 0.64 away from 80% or 0.80? All right. So that's what we're going to calculate next, is how many standard deviations away. And that is what's called our standardized test statistic, or our z. All right. Remember, we're working with p's, so we calculate our z. And we would use that then to find our p-value. So we determine how far away a sample value is from the null hypothesis. We find a z-score. This z-score is called the standardized test statistic. All right. To get the p-value, we find the area under the normal curve from the standardized test statistic and farther away. For a two-sided test, we double our answer. All right. So what we're going to have, I don't think I have this on the next slide. Let me just check. Okay, just checking. So what we're going to have is we've got our distribution with 0.80 in the middle. We got, 0.64 here for our sample. That was our p-hat. This was our mean of the sampling distribution, what we think it is. So we're going to figure out how far away is that, how many standard deviations away this is. And that's going to be the z. And then we find this area down here. And since it's normal, we can, normal CDF to find that area. All right? The lower bound would be something small in this case. The upper bound would be the 0.64. The mean would be the 0.80. And the standard deviation would be what we got from the last slide was 0.0565 and so on. All right, and that would give us our p-value. All right. Now, if it was a two-sided test, so this was just if we had our alternative hypothesis is that p was less than 0.80, which is what we had it was. All right, so if our alternative hypothesis was that p is not equal to 0.80, then we would have to double it, because then we would also have this side to look at over here. All right, so it's a weird thing we do. So if we have not equal to, we double our p-value. All right, but if we're going to do the calculator test, it's going to automatically calculate it for us anyway. So it is built in the calculator, and I'll show you that here in a minute. All right, so in the preceding example, an administrator at a local high school decided to perform a test at a 5% significance level, with the null hypothesis was 25% of students had jobs, part-time jobs, and the alternative hypothesis was that our school, it's less than 25%, where P is the true proportion of all students who have a part-time job. The administrator selected a random sample of 200 students and found that 39 of them had a part-time job. We already confirmed the conditions were met. So we did the conditions on the last video. So explain why the sample gives some evidence of the alternative hypothesis. Well, let's look at what our p hat value is. It is 39 out of 200. If we do 39 divided by 200, that is I think that's 0.195, which is definitely less than 0.25. So this is some evidence for the alternative hypothesis. Like if we got that this number was like 0.30, that would give us no evidence, right? Because it would already be bigger than that. So this is some evidence for the alternative, but is it significant? So is it far enough away that it is a lot of evidence? So what we do is we calculate the standardized test statistic, or the z-score for that, and the p-value. So the way we do that is, let's see, we're at 0.195. We want to know how far away is that from 0.25. And we divide it by that standard error, or that sampling standard deviation we use, which is 0.25. 1 minus 0.25 divided by our sample size, which is 200. All right, so if we pull out our calculator and calculate that, let's see, we've got on top, we've got 0.195 minus 0.25 divided by second square root 0.25 times 0.75 divided by 200. And now this will tell us how many standard deviations of the sampling distribution it is away from the mean. It's negative 1.796. All right, so it is less than, so it is below the mean. And now we want the p-value, so we got to think about it. Remember, we're working with this normal distribution. Our mean here would be 0.25, and we're way down here at 0.195. All right, and we want to know what's this area down here. Well, we've already found the z-score, so we can use the standard normal curve and that z-score. So we can just use normal CDF with a lower bound of something really small, like negative 100 or negative 1,000. Our upper bound would be the negative 1.796. Our mean would be 0, and our standard deviation would be 1. Or we could use this data and this as our standard deviation and do the same thing in the normal CDF. But we've already got the z-score, so let's just try and do it that way. Second bars, normal CDF. We're going way down. Yeah, that number will work. That's way down. Negative 1.796 is our z-score. We're going from 0 and 1 because we're working with our standard normal curve. We're working with z-scores. And we get that our p-value is 0.036. All right, that's pretty small. So now what conclusion should we make? Well, it gave us our alpha right here. All right, so our p equals 0.036 is less than 0.05, which is our alpha. So remember, when p is low, it rhymes, remember? Reject the hoe. So we are rejecting that p equals 0.25. In other words, we have evidence, and we have significant evidence that p is less than 0.25, our alternative hypothesis. All right, we'll add some context in later, but that's basically what we're going to be doing here. All right, so makes 35 out of 50, so I think I changed the number here, and our null hypothesis was that he makes 80% of his shots. What is the standardized test statistic? So what is the z-score going to be? If you want to pause it and do it on your own, go ahead and pause it and do it on your own. I'm going to start working it out now. So let's see, 35 out of 50 is what, 70%? So it's going to be 0.70 minus this P naught, which is 0.80, over the square root of 0.80. 1 minus 0.80 is 0.20 over 50. And we're just throwing that into our calculator. So let's see, we've got in parentheses 0.70 or 0.7 minus 0.8, 0.80, divided by the square root of 0.80 times 0.20 divided by 50, and that should give us our answer, negative 1.767. Oh, is this the same as it was before? All right, maybe there was an 8 after that. All right, so but that is what it is. There it is. All right, we keep the sign with it. It is negative because it's below the mean. And there we go. All right, let's try another one. What's going to be the p-value then? So now we've got that our z is negative 1.768, I guess is what it rounded to. And we're going to be going down from there. All right, so we're at this normal curve. We got 0.80 here, and we're at 0.70, and we want to know this area here. Or we can think about it as the standard normal curve with 0 in the middle, and we're down here at negative 1.768. And we want to know this area down here. Either one of those would be the p-value. All right, so we're going to go into normal CDF. Our lower bound is going to be something really small. Our upper bound is going to be, we can use the z here, negative 1.768. Our mean, if we're going to use this, would be 0, and our standard deviation would be 1. We could also use this data up here with the other mean and standard deviation we got. But let's see what works out. So second distribution, normal CDF, big negative number, negative 1.7. Oh, that was slightly different. So 6, 8, and 0 and 1. And we get 0.0385. And look, there it is right there. All right, that seems pretty low. So we'd probably end up rejecting that null hypothesis. All right, so that's it for that one. Next one, we put it all together in one big hypothesis test. We do our state plan do conclude.